In this video we're going to look at the Fourier and Laplace transform, so we're going to look at it in a kind of operational sense, meaning that we're not going to get into it in mad detail. I do have another course here called the Fourier and Laplace transforms that goes into all the mathematics in glorious detail. Also describes it in terms of a geometric method. So if you're interested in finding all the details, I suggest you can go and have a look at that. Okay, so if we had say a sinusoidal signal here, then it's quite easy to get an idea of frequency. So if we say this is signal repeats 50 times every second, so it's got 50 Hertz, then if we were to look at another signal there, let's say this signal here repeats every 100 times a second, so it's a 100 Hertz signal, then you can get an idea of the frequency. You see this frequency here is higher than this frequency. So another two things we're interested in sinusoidal waves is the amplitude. So there's a height from here to here. Okay, we'll call that V0, and that's the peak amplitude, and the peak to peak would be the here up to this point up here. Okay, so one other thing we're interested in is the phase. So if we were to allow this signal to range in time, then it would shift along in time, and when it shifts along in time, the phase of this would change. Okay, so that's a different, same signal, slightly delayed, meaning there's a phase shift. So if we were to represent these three things all together in one graph, then what we could do is we could draw a kind of three-dimensional graph. We could say we could have a V out here, and we could call the V out along that axis there as well, and we could put an axis along here and call it the frequency axis. Okay, so each point here represents a higher frequency as it goes along that axis. So we're going to have to represent three different things on this little graph. We're going to represent the amplitude. So this is the amplitude here. So this is easy enough. We just take the height up there and we'll call that height V0, and we can represent the frequency by just choosing the particular point along the axis at that frequency. Now there's one other thing we're interested in is the phase. Now what we could do with the phases, we know the phase is going to be represented by an angle. Okay, so the angle is going to be between say 0 and 360 degrees. That's if you're doing it in normal degrees. So what you could do is you could think about this height here as actually rotating round about this frequency axis. Okay, so imagine a point here rotating around the frequency axis, and if you take this axis here as your 0 degrees, then we would go around 90, 180, 270, then 360 would be all the way around about. So you can imagine this little phaser, if we call it that, rotating around this axis at 100 times a second. That would rotate around at 50 times a second. Okay, now, and I've just drawn out the actual phase angle there. So the phase angle would be given by this little angle here. So this cross here would be us looking in from this angle in here. Okay, so that's one way we're representing this signal here. Okay, but we don't tend to write the signal in terms of degrees. We tend to use angular frequency in radians. Okay, and the actual where you're going to use the angular frequency, which would radians per second. So the question is then, why bother introducing radians? Why don't just keep it using degrees? Okay, well the answer to that question really is that if we work in radians, then by working in radians we've got a method of directly relating angles to lengths. Okay, and as a consequence of this, most of the maths that we're going to use in terms of calculus is done in radians. Okay, so here's an example here. So if we had an axis system, x and y axis, and we had some little phasor there in yellow, so that phasor there is the same as this one here, it's just rotating around a circle, and the angle here is it's theta in radians, then we can get the length of the arc. The length of the arc is simply going to be the length here, if we call that length L, times the angle theta. Okay, so that means that we can directly relate the length here with an angle there, and it's simply related through this simple equation here. The length of the arc is going to be L times theta. Okay, now what is a radian? Well, a radian is 1 radian is the angle subtended by an arc equal in length to the radius. So we'll see that in the next page here. So if we were to take the radius of a circle and we make that radius there equal in length to this arc here, then we'll get this angle here, which is 1 radian, which turns out to be about 57.3 degrees. But it doesn't matter that it's 57.3 degrees. We really want to get away from talking about degrees. We want to talk about in terms of radians. So we know that the circumference of a circle is going to be 2 pi r. So if we say let r equal 1, then we could say the circumference equals 2 pi. Okay, so it's going to take 2 pi of these radians to go round 360 degrees. Okay, so take a bit of time and think about that and convince yourself that that is correct. So we replace the frequency f by the angular frequency omega, which is 2 pi f. Okay, so now the angular frequency is in radians per second, as opposed to what we had previously in hertz, it's revolutions per second. Okay, so we can rewrite that. We can actually write everything out that we've learned so far in one simple equation. So you can say that the voltage at time t is going to be v naught, which is the amplitude. That's our sinusoidal signal. The frequency is going to be in terms of radians per second, so it's going to be omega times t plus some phase angle phi, where omega is equal to 2 pi f. Okay, so that's a little equation there that defines sinusoidal input, and it tells us about the 3 components: the amplitude, the frequency, and the phase. So if we were to try drawing this out, as I said, we could put along this axis, rather than having frequency, we could have omega along this axis and this axis here. Well, these are the same axis really. They're just going to be a voltage. Okay, so it's a value of V. But what we're interested in is not representing it in a 3-dimensional format here, because it gets difficult to try and draw out 3-dimensional drawings and obviously get information from those. So we want to represent it in a simpler format. So, well, here's a simpler format thing, something that we could do. We could take all of these lengths here of these phasors and we could turn them up so that they sit along just this one axis. Okay, so that's what I've done here. I've just taken all these phasors and shifted them round so they sit up in this axis. Now the height of these phasors here is actually going to be the length here, so it's that blue length. Now that blue length there is going to be, according to Pythagoras, it's going to be that squared plus that squared, and you're going to take the root of it in order to get that height there. That's why whenever you see this frequency plot, we'll have the frequency along this axis, but it'll be the magnitude of the voltage up this axis. So that magnitude is this length here. Okay, so we have to also represent the phase at each point. So the phase is easy enough. You can think about a frequency axis along here, and the phase, well, the phase can change. It can go from our 0 degrees round to our a plus 90 and round to plus 180, sorry, and round to minus 180. So I'll just change that just now, so it says that. So it's going to be plus 180 and minus 180, so that will represent it going round a full circle. Okay. Okay, now, so when we work out the frequency here, sorry, the phase here, we could simply take this point here and we say, well, if this length line here represents the 0 angle, then that would be sitting at 90 degrees. So you could put a little point up there, 90 degrees for that one, and this one's a bit less than 90 degrees, that one's even less, that one's a different height, so it's a different angle again, and we can go along and plot the angles. Of course, if we had one sitting down here, then the phase angle would be down below the line here. Okay, so we split this into two graphs, a frequency and a phase. Now, for anyone who's been done some electrical engineering before, we're maybe looking at this and saying, well, yeah, that sounds reasonably familiar, possibly, but where are the complex numbers? You like looking at it thinking, I thought we had to be dealing with real and imaginary parts of complex numbers, and this axis here would be a real part and that would be an imaginary part, but I haven't got any of that here. Well, for the moment, in order to describe this, all we have is just that one equation there. That equation's not got any complex parts to it, and all we're doing is representing that equation there in this graphical format. So this is perfectly correct what we've done, but we don't tend to look at it in these terms. We tend to look at it in terms of complex frequencies, and you're probably maybe wondering, well, why bother? Why don't we just keep it simple like this and we'll forget about complex frequencies and the Fourier transforms and Laplace transforms? So that's the kind of question I'm going to go and answer now, okay, and we'll have a wee look at the Laplace transform and the Fourier transform as a consequence of it. So first of all, I wanted to try and get back to some basics here. Okay, so we're getting back to basics in terms of what our signals are and why we represent them in terms of Fourier and Laplace transform, but I thought we'd just go back right to the beginning and we'll have a look and see what do we mean by our basic components that we use in electrical engineering. So we're interested in resistance, inductance and capacitance, and we're also interested in voltages and currents. Now, the reason for introducing the idea of the Laplace transforms is that it makes it easier to solve differential equations. Okay, so how do the differential equations occur in the first place? Well, when we have an RL and C, we're dealing with electricity, so there are only these three fundamental components: resistance, capacitance and inductance. Okay. Now these have an analogue in mechanical systems, so the resistance there would be equivalent to a friction or heat loss in a mechanical system. Inductance would be equivalent to a mass or an inertia in a mechanical system, and capacitance would look like a kind of spring or energy storage in a mechanical system. Of course, this mass here, which is inertia, that would be look like energy storage as well, because the energy is stored in the inertia of the system as opposed to the springiness of the system. Okay, so that would be equivalent to looking at a spring with a mass attached to the end. So the mass has got some inertial energy, and the spring's got some potential compressive energy associated with it. Now you might be saying, oh, but what about all the other elements we have? We can have diodes, transistors, and we can build up other circuits with op amps and things. Well, all those other circuits are made up from those basic constituent, or can be described in terms of those basic constituent parts: the resistance, capacitance and inductance. So that these three things are quite fundamental. Now we're also interested in voltages and currents. Now again, in terms of a mechanical system, we can say that the voltage is like a force and the current is like a velocity or a movement. Now, we talked about there being differential equations associated with these problems. So if we were to take RL and C and we're looking at saying how RL and C affect and are affected by voltage and currents throughout a circuit, we're going to end up with a differential equation. Well, we'll see that just in a minute as an example, but if we were to take the three equations, and these are the only three equations we're actually interested in. So resistance is equal to the voltage divided by current, that's Ohm's law, and these are to be accepted. I'm not going to go and prove these. And the current is equal to the capacitance times the rate of change of voltage with respect to time, and the voltage is equal to inductance times the rate of change of current with respect to time. So You can think about this here as Ohm's law, so it's a measure of the heat loss or friction within a system. In this instance here, if we think about C, if C was say very large, then if we were to take C down here, we would have one number divided by a very large number, which would be very small. So it meant that dV by dt would be very small. So we're saying that the rate of change was small. So we say voltage would change very slowly with respect to time. Okay, so we would be looking at that as a kind of a very stiff spring. And if the value of C was very low, then voltage would change quickly with respect to time. So that would be a spring that isn't stiff. Okay, so if we were to then look at inductance, if inductance was very large, then we would have V upon L would be a very small number, so the rate of change of current with respect to time would be very slow. So we would see that then as in that case would be L would be large, it would be equivalent to have a large mass, or a very inertial system. If L are very small, then it would mean that we would have V upon L be very large. So it means that current would change quickly with respect to time. So it means that it'd be a low inertial system or a low mass system. So these are direct analogies within the mechanical systems. Now, what we're interested in is these two equations here, because they've got differential parts to them. Okay, so differential equations. So we can say that I is equal to C dV by dt, but we might be interested in actually the V part of it. So in order to get the V part, we've got to integrate both sides. To integrate both sides, we get 1 upon C, the integral of I dt equals V. And again, the other way around about here, we've got V equals L di by dt, but we might be interested in the I part of it. So in order to get the I part out, we have to integrate it, which will leave us this 1 upon L, the integral of V dt equals I. So that means that potentially we could have an equation that's got R, L and C's in it, okay, and also the equation is going to have potentially dV by dt's and di by dt's, and it's potentially going to have the integral of the I dt, integral v dt's in it as well. So it's going to be an integral differential equation. Okay, so let's have a wee look at a typical example. So here's a wee simple example. We've only got an L, a C and an R, and we've got an input voltage V in, output voltage V out, and we're interested in this V out here. Okay, so in order to get that V out, the V out here is equal to IR, which is the volt drop across this resistor, plus L di by dt is the volt drop across this resistor, and the 1 upon C integrals is the current through IR is the volt drop across this capacitor. Okay. Right, so we end up with this. We end up with these integral differential equations, which are awkward to work with and difficult to solve sometimes. So we're really looking for a wish list. Now our wish list is we don't want any differentiation, we don't want any integration. Also, we want to be able to represent our amplitude, frequency and phase in terms of what we had seen previously. So we want it to be able to still represent our signals in these terms. Now the Fourier and Laplace transform gives us all of these things. Okay, so we're going to think about this in terms of a bus analogy. Now, when I was at uni and I was learning this, I was never happy with it because I wasn't sure where it came from. It just seemed to be a bit of a cop-out and I didn't really understand it. I could work the maths, but I couldn't understand what I was doing. Now, I talked to one of the lecturers there at that time, and he gave us this analogy, and he did say that if you don't need to know how an engine control management system works on a bus in order to take the bus to college. Okay, you just need to know where the bus stop is. You need to the right amount of money, and you need to get where to get off. Okay, so we're interested in this, and we think about the Laplace transform only in terms of this systems method. Okay, so we don't need to get into the details of exactly how it was derived, who derived it, and the context within mathematical context with the derivation. Yeah, we just need to know how to drive this little bit of mathematics. So if we had this voltage at time t is I times t times r, and this other equation there, that one there, then that's going to give us Vs ISR, Vs LSI, it's going to be that. Okay, so it means that the differentiation here is equivalent to a multiplication by s, and integration here is equivalent to a division by s. Okay, so it means that we can replace differentiation integration with multiplication and division by s. So it means that we can take complicated functions, right, and let's get integral differential parts of it, and we can represent them just in terms of simple algebraic functions of s. Okay, so we can end up with that. For example, there that the complex impedance is going to be given by r plus ls plus 1 upon cs, and we can mess about in this domain, okay, which is the complex frequency domain, and then algebraically we can manipulate the equations, and then after that we can do the inverse transform and get back to the time domain representation. Okay, so it just makes things a lot easier, quicker and simpler, and that's what the Laplace transform does for us. Okay, so we've got one part from the wish list. Now the next part from the wish list is to represent the amplitude, frequency and phase like we did previously, but now in terms of our complex frequency, and we're able to do that here simply by these couple of identities. So e to the I theta equals cos theta plus I sin theta, so we could replace that theta by omega t, so you get cos omega t plus I sin omega t. So really what this looks like is we have a frequency axis here, omega, we have a real part of the frequency axis and an imaginary part of the frequency axis, and this e to the I omega t looks like a phasor which is rotating round about the omega axis, and you can see it rotating there. Okay, so this here in effect it replaces what we have at the beginning, which was our V2 and V1. Now these axes here, they're actually real parts and imaginary parts of a complex frequency. Okay, so this is different. This is different from having a real and imaginary complex frequency, but it looks the same. Okay, and all of the mathematics works out the same as in this simple case here. Okay, so that's us got really the two factors that we really are looking for. Now the last little bit is to look at poles and zeros. So if we had the complex frequency domain, so we would have a sigma and a j omega here, and if we were to have a pole, say somewhere up in this sigma axis, so this would force this plane up to infinity at this point. And what we could see, if we could think about this in terms of some elastic surface, then if we move down the sigma axis to sigma gets to 0, then we'll be on our purely our frequency axis. In that case there we would have a raised section here, which in effect would be our low pass filter. And if we were to draw it out here in this section here in 3 dimensions, we would have an imaginary part, a real part, and our j omega axis. But also note that we can't actually draw it like this on this graph here because we don't have enough axes, because this axis here isn't the imaginary axis, it's the value of a sigma axis. Okay, so but we can take this slice here and then represent this slice here in a 3-dimensional sense here, so it's equivalent to having our phasors rotating round about on the j omega axis here in 3 dimensions. But of course we don't draw it in 3 dimensions, we always put it into an easier to understand 2 dimensions, which is the magnitude of these blue lines here. So the magnitude really is by Pythagoras, it's going to be this distance squared plus that squared, and the root of it will give us the magnitude or the height of these phasors here. So in effect you're taking all of these and you're rotating them back on to just the real part of the axis, and then you're going to have the angle there that these phases are represented by the phase diagram here, where that's our value of omega, again our frequency, and our phase, which will that can rotate actually between, in this instance, be plus 180 minus 180. I put 9, it should be 180. Okay, so that's all there is. It's quite a brief introduction to Laplace and Fourier transforms, but I think it gives a good deal of information that will become useful to us later on in the course. Okay, so thank you for listening, and I'll get you on the next video. Goodbye.